My name is Ben. I am a principal engineer at Intel, where I work with Luke on firmware. We work in the chipsets group on the power management, so the part of the chip that controls power to all other parts of the chip. So, we control a lot if you think about that. And this talk is called Applicative, short for Applicative Functor, as some of you may know, the forgotten functional pattern. Now, a couple of disclaimers. I feel like I have to disclaim this. I did not use any AI in the preparation of this talk. So all the mistakes are mine. None of the mistakes belong to ChatGPT. All the code you're going to see, I have compiled at some point. I may have made errors in translating it to slides. Please answer any questions as we go, and I'll either please ask any questions. I'll either answer or defer them in some way. My hope with this talk is that you can go home after this talk and look at your code, perhaps with new eyes. This is one of my favorite quotes. So let's jump straight into it. To start with, although I know at this conference in particular, many of you may be familiar with functional patterns, I just want a quick refresher. We hear a lot about Functor, we hear a lot about Monads, so we'll just do a quick refresher on that, and I'll show you where Applicative fits in. First, if I can see, I want to do a quick sort of survey. So how many people would answer yes to one of these? So people who've heard of these patterns, but that's about all, haven't used them. A couple of people. People who kind of understand how they work. Yeah, that's a lot of people at this conference. People who don't see many use cases for them. Maybe a couple, maybe not that many. People who have written code that uses them and found it good. Yeah, that's a good amount at this conference. People who completely understand all of them. Yep. I see Lisa at the back, yes.
I may be stretching a little.
And people who could say this, Haskell informs all my APIs. There's a few at this conference, I know that. There may also be some people who've had this experience. Well, I thought I knew until you just said that. Okay, so we'll go through. And I would say really, don't worry about the is here. Just the way to look at these functional patterns is think about what they do, right? Okay, so here's a review. So functors, many of us at this conference in particular know, functors in a simplification are in C++ a parameterized type, so a class template where one argument is free. So the canonical example perhaps is optional. Vector is also a functor, and sequences, ranges in general. And expected is a class template of two arguments, right? But if we bind the error type, typically we bind the error type, and then it's a functor, right? Because one of the types is left free. And the characteristic function on functors is fmap. And this is what fmap looks like in C++. I hope that slide is visible colors. So takes a function, takes a functor. So I'm just going to explain most of these things in terms of optional, because that's the easiest way to explain. So it takes let's say an optional int and a function from int to string, and it will give you back an optional string. That's what it looks like in C++. In Haskell, the type signature looks like this. And for this reason, I will be using Haskell type signatures to explain, because you can see the difference there. So this is so fmap is also spelt with this funny $ glyph when it's used as an infix operator in Haskell. You might see that in a couple of slides. But what this function signature is saying is it takes a function from A's to B's and a functor of A's, so optional A, and returns an optional B. So if you're new to Haskell, if you've never seen Haskell type signatures, this is how to read them. We have the function, then the double colon, you should read has type. And then every argument is separated by an arrow. And the final argument is the return type. And then so we can look at arg1, arg2. Where you see f, that in C++ is the class template, that is the functor. And the A is the value type, or the B is the value type. Or indeed, the function from A to B is the value type here, right? So everyone good with that? I want to just put that in just so that we can follow along. Okay, so that's functors. Now the other type class you hear about, the other concept, if you like, that you hear about is monads. So a monad is very similar to a functor. Indeed, every functor is a monad. Did I get that right? Every monad is a functor. Yes, I saw Steve raise his hand. Every monad is a functor. So the familiar examples of functors also happen to be monads in C++. Again, optional, will be the sort of poster child. And the characteristic function on monads, well, there are a couple of ways to formulate it. Oftentimes we say it's bind. Join is an alternative. And so bind looks very much like fmap. The signature in C++, very much the same, except the function here returned, instead of being a function from A to B, it's a function from A to a functor of B, right? So it's a function that returns an optional instead of just returning a string, right? And monad, this characteristic function on monad bind returns the result of applying the function to the thing inside the functor again. But this time the functor returns an optional. Okay, so in Haskell, bind looks like this. And in a couple of slides, I'm going to flip these arguments around to show kind of how fmap and bind actually compare. So M here is the same thing as F. It's just instead of a functor, it's a monad. But it's, again, so optional A, function from A to optional B, return optional B. And sometimes you see it spelled with this glyph when it's infix. All good? OK. So you may have noticed, if we were to use fmap with that function that returns an optional, we'd end up returning an optional, right? That's what bind does. It collapses that back down to a single optional. And that's why join is sort of alternative. Like you put fmap together with join, and it becomes bind. And these are the Haskell function signatures involved. I'm not going to go over them too much. But basically, that's the way to think about it. Now, here are the signatures all stacked up together so you can compare them. The top two are just the same. That's just fmap and infix fmap, right? So takes a function, optional A to optional B. And then bind, and I've just flipped around the arguments just to show you the symmetry here. Bind takes the function that returns the optional, and optional A and optional B. Now in C++, since 23, with 23, we got monadic functions for std optional. And fmap, we spell transform. This is a member function on optional. And this is what std CP reference says about it. If this contains a value, if the optional is engaged, we run the function on whatever's inside and return the optional result. This is fmap. And likewise, we have a function called and then, right? It's the same signature as transform, but this time the function has to return an optional, right? So this is bind. We have transform and we have and then, and that's how in C++ on optional we spell fmap and bind. Okay, so far so much review for many folks. Yes? Yes? Good. Everyone good? No questions yet. All right, so where does applicative come in then? Well, in the early days, Haskell only had functor and monad. Going back to the mid-90s, these were both in the Haskell report, and Haskell has, we won't worry about the I/O monad in this talk, but Haskell has I/O list, which is like our vector or range, and maybe, which is our optional. So this is Haskell as they start out. And then sometime in the mid-2000s, and in a paper in 2008, particularly popularized, we see Applicative show up. And for a while, there was this kind of relationship, right? So these are like, in Haskell, these are type classes. You can think of them as concepts. And this is something like concept subsumption. So monad sort of inherits from functor. And applicative also inherits from functor, but separately from monad. So this was the case for a while. Now, of course, as I said, every monad is a functor, and every applicative functor is a functor. But then in the mid-teens, there was a proposal to restructure this hierarchy and interpose applicative in between. And today we have this structure in Haskell. So every monad is an applicative functor, which is a functor. And of course, then we get the functional monadic patterns we've seen. OK, that was end of part 1. There are several parts here. OK, so now we know sort of where applicative fits in. It's in between monad and functor. But probably that doesn't mean much to you yet because there's no context behind that. So let's have a look at the mechanics of applicative and how it works in C++.
Way ahead of you on this one.
OK, so here is a very brief survey of talks that I dug up. There might be more, but these two in particular are out there. And at this conference, David Sankel gave a talk in 2015, which he repeated at CppCon 2020, an updated version, naturally. And Michal gave a talk in 2015 CppCon. And what they said was this, because when you look at Haskell, you see this. And basically, all existing C++ work on applicatives says this. So we know that fmap applies a function to the optional. I'm going to say optional, but you should think any functor, right? If you have a function inside an optional, then that's what applicative is for. This is what, if you Google it, this is what you will find out. And apply, again, is spelt with this funny star operator. Or sometimes called app to distinguish it from like applying functions in general. So everyone explains it like this. And then they say, almost as an afterthought, this can be used to apply functions in more than one argument. Well, that's what I want to highlight in this talk, because this is the entire point of applicative. This can be used to apply functions of more than one argument. And this is actually what we need in C++, right? This is what applicative does. It generalizes fmap, right? Apply generalizes fmap. So, we can think about how would we write functions of more than one argument? What would the signatures look like? Because that seems like it would be useful, right? So fmap1 here is fmap, is transform on optional, right? fmap0 is, well, it takes an int and makes it into an optional int. It's just constructor of optional, I guess. fmap2 takes 2 arguments, or a function of 2 arguments, and 2 optionals, and combines their internals with that function. fmap3 and fmap4 and fmapn, right? This is why I use Haskell type signatures, because I can actually fit them on the slide. OK, so then this is what we actually want to do. So then why does apply look like that? Well, the only real reason it looks like that is because of the mechanics of Haskell, right? And as a C++ programmer, when you learn about applicative and someone tells you, well, it applies a function inside the optional. And you're like, OK, I understand that. Wait, I'm never going to use that. When do I ever have a function inside an optional? This is not really helpful for us in C++. But we should remember that the point of apply is to be able to apply functions of multiple arguments. It's only this way because of Haskell, right? Because Haskell doesn't have functions of more than one argument in a very literal sense. Every function in Haskell is a function of one argument. And that's why Haskell type signatures have arrow, 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 rather than comma arguments, arrow, return. Right? Because Haskell has built-in partial application, built-in curried functions. All functions in Haskell are unary functions. And when you call an n-argument function with one argument, you get back an n-1 argument function, right? So this is why applicative has this form. So, just a quick look at how this works in Haskell before we get more into C++. So the plus function is a function of 2 arguments. In this case, I've monomorphized it to int. In Haskell, just is like the constructor for their optional, which is maybe, right? So if we fmap plus onto just 1, we get a function inside the optional, right? It's partially applied that function with fmap. And we do actually get maybe function of int to int. And then we use apply on fmap plus just 1, and we apply it to another optional value, another maybe value, just 2. And that gets us back the maybe int, right? That's why apply looks like that in Haskell. And you know, there's a symmetry between how you apply regular functions, and I've put plus in prefix form here just to make it clear. So when we add 1 and 2, naturally we get 3. That's sort of regular plus. When we add just 1 and just 2, we put the apply infix in between them, right? We can either say plus fmap, just 1, or we can say pure plus to put the function inside the optional, as it were, and then apply, apply, apply. And every time we apply, it takes off 1 extra argument, right? So it's eating 1 more argument, eating 1 more argument. And you're getting at each intermediate stage a function of 1 less argument inside the optional, inside the maybe. Question.
Can you go back 1 slide?
Yeah.
Why is the type on line, I guess 2, why is it maybe int to int instead of int to maybe int?
OK. So the function is int to int to int, right?
Right.
So when we apply plus inside the optional, we're going to get, it's just the way the types work out, right? We're going to strip one of those ints off and return the resulting, this is the return type of applying plus to 1, right? You get back a function, it's like the add 1 function that you get back, right? This is the add 1 function. And that's inside the optional.
Oh, I see. So depending on whether there was, depending on whether you gave it something or nothing, it may or may not give you a function.
Yes. So if you gave it nothing here, you'd get something of the same type, but its value would be nothing. It'd be the empty optional.
Okay.
Right? But it'd still be optional int to int.
Got it.
It would just be empty. OK, cool. All right. That's probably about enough Haskell for now, I think. That'll do. Now, here's more surveys of existing work. And the reason this talk came about, I'm very happy Barry's in the audience. The reason this talk came about was I was reading papers, and I was noticing that they didn't really ever mention applicative. They mentioned Functor a lot, they mentioned Monad a lot, but all these papers which, you know, on the face of it have a lot to do with monadic things, they don't say anything about applicative. In fact, in Sai's paper for monadic function instead optional, they say, I couldn't think of any use cases of this. Well, that's why I'm giving this talk. And in particular, I want to look at what happens when we use applicative on stood optional, on stood expected. And let's have a look at how that works in C++. So there is a paper which is proposing an error propagation operator, P2561. And it posits the following code. So we have a couple of functions that, you know, these doesn't matter what these do, but they're from int to expected int and some error type, right? Got a couple of functions. We want to call these functions, one here. And if they both are engaged, if they both succeed, we do something with their results. We format them, right? So real simple function. And what this paper is saying is like, this code is, you know, it's OK, but we have to do like manual control flow here and manual stuff here, and it's not real great. There are a couple of, was there a question? No. There are a couple of, you know, the paper goes through a few things. So how do we do this today? Either we do manual error propagation, like you just saw, this kind of stuff, or a bunch of libraries like boost outcome wrap stuff up in macros. We can get nice syntax if we have, if these things, instead of being expected, if these things throw exceptions, right? Because this looks like straight line code. You don't have to worry about this. This thing just throws an exception, and therefore this function throws an exception. Or we get nice syntax with coroutines as well. But you know, the underlying sort of unstated thing there is that both exceptions and coroutines may entail overhead that's unacceptable to some. And so the paper says the best case today involves macros. Well, I wanted to see if I could make a better case, a better answer to this question. So Sai said that they couldn't think of many use cases, but then Barry wrote this paper, and I think this is a use case for applicative on optional. So let's try and answer that question. Let's try to write a nicer looking way to handle that code that you saw before. Applying a function to multiple possibly failing, calling multiple functions that possibly fail and then applying those together. And our goals are these goals. I think these are good goals. I mean, you may have different goals, but these are my goals. So let's not go straight to expected. Let's start off with optional. Now, the first observation I can make is that this can totally be solved with monadic functions on optional. Who likes this code? Only the people who are really into functional programming. This doesn't look great, does it? I mean, in C++, this isn't great. So this is how I rate this code. How did we do? Well, there are no macros. That's great. Manual control flow, ish. It's not declarative. It's very imperative. Good-looking code, no. Efficient, fairly, I'd say. It's okay. It's good. It's fine. But let's look at an applicative solution. Well, the simplest thing to start out with is we can try and do it. Let's try and do it like Haskell and see where that gets us. And spoiler, there are better ways that we can do it. But Steve was saying to me the other day, it's hard to think of how to work an applicative without having partial application. So let's try partial application. So here's a curry function. It's a function that I have my meetup to thank. Jason Turner and Vaughn Cato and myself sort of cooked this up during a meetup talk, during an online meetup. So what does it do? It takes a function and some arguments, and if you can call the function with those arguments, go ahead and do that, right? It's the first bit, no problem. If you can't, we're going to return a lambda, which captures the function and captures the arguments. And when we call that function with some more arguments here, it's going to return a recursive call to curry, right? So this recursive call will end up calling the function eventually when it has enough arguments. Everyone following this? Something you may be new is deducing this. This is a great use case for deducing this, so that we can perfectly forward the arguments just like the value category of the lambda. In fact, this was my original use case for deducing this. Yes, this sort of stuff comes out of my meetup. If you don't have a meetup, feel free to attend the Denver C++ meetup online. OK, so let's try that out. This is what our fmap function looks like for optional. And I should say, for those new to functional programming, there's not just one fmap function. Fmap and bind and that, they're differently implemented for every kind of monad that you have. So this is the particular one for optional, right? But it's fairly simple. We have the function, we have an optional coming in, and we're going to return the result of currying that, right? So we potentially are returning a partially applied function inside the optional. That's what curry gives us. And we do the obvious thing, right? If this optional is engaged, we're going to go ahead and call the function, always remembering that might be a partial application. But if it's not, we're going to return empty optional. And then here's app, the characteristic function of applicative. I call it app to avoid clashing with apply. And it looks real similar, right? The only difference here is that here, again, like Haskell, the function is inside the optional. So we have to check that they're both engaged, and then we do the call, right? Everyone good with that? OK, I see thumbs up. So let's try it. Well, this is what the code looks like. It's, depending on what you think, it's a little bit better than before. We don't have manual control flow here. We're not allowed to parse in std format and take pointers to things in the standard library, which is the only reason I wrapped it in a lambda here. But if you were allowed to take, to parse that as a it's not even a function, it's a function template, right? So we can't pass it. But that's why the lambda's wrapping that. That's the only thing there. And then we fmap we pass foo to the lambda with fmap, and then we pass f, and then we pass b to the resulting curried function using apply. Yes? All good? Still good? So how did that do? Well, like I say, I think a bit better. More declarative, no manual control flow. I think we can still do better on the good-looking code and efficiency front. Yeah, we had none of that stuff. It's not bad. Yeah, we did wrap std format in a lambda because we can't actually parse it, curry it directly. The prefix syntax is a bit awkward. Don't worry, I'm not going to be doing much operator overloading. But this was us trying out the Haskell method, which I think is kind of the naive method that most people would try first. But we're in C++. We have functions of more than one argument. Asterisk. We don't if you look at it functionally, but never mind. So let's try making fmap variadic. We can do that in C++, right? And it's actually fairly easy. We can say, let's have it take a pack of optionals. And we can write a fold expression here. And then we can invoke the function with them all, right? Just the same. We don't need curry anymore. Now notice, someone asked me after I gave this talk at my meetup, someone said, you said applicative and then you end up using fmap. What's with that? Well, this is not the same as optional transform, right? This is not a member function of optional for a start. This is not a function of one argument. This is qualitatively different, I would contend. So what does the code look like now? Well, quite a lot better. I mean, slightly better than the previous one, but I think quite an improvement over the original, right? We still have to, this is using std format, so I'm really taking my lumps here, right? So I have to wrap in the lambda, but in general, this could be a function in my code base, which I can actually pass, right? That's just an artifact of using stuff in the standard library. But I think this is pretty nice call. We're just saying, apply this function to multiple things, right? So how do folks think we're doing? Yes, question.
Technically, haven't we slightly modified the behavior since the original didn't evaluate bar?
Haha! Yes, we have. Is it still efficient? Thank you for asking that question. Yes, because of course we have modified the behavior. If foo fails in our version, we don't return here like the original. We still go on to evaluate bar, we still go on to call this thing. Even though in the end, we would get disengaged optional, we would get nothing out. We are still evaluating things after this. That's why I give talks at C++ now, because the crowd is a great straight man. All right, so this is a fundamental issue, right? And Haskell is lazy by default. C++ is not. If we want to get around this and still be declarative, we need a way to evaluate function arguments lazily. So let's try that and see how it comes out. I want the code to look something like this. This is probably the best we can do at the call site, I'm thinking, in C++, right? So we're going to do a lazy call of foo with I, a lazy call of bar with I, and we're going to pass those into fmap. Now, what does lazy call do? Well, it returns a lazy, whatever a lazy object is, right? We're going to fundamentally, to evaluate a function argument lazily, we're going to wrap it in a lambda, which, when we evaluate it, will return it, right? That's the idea here. So here's the lambda, which is this f here. Don't get confused. This is either foo or bar, right? This is going to evaluate foo and bar when we want it to. And there's this lazy object. So next question is, what does the lazy object look like? Well, it's going to capture, here's the lambda, right? It's going to fundamentally be this lambda. And it's going to keep this, the result of invoking the lambda, which is an optional. We know it's an optional in this case. When we ask it if it is true in that fold expression, that's when it's going to invoke the function and tell us if it succeeded, right? And then, given that it's true, we're going to dereference it and get the actual value out that the function returned. Okay, and fmap looks the same. It's just that the fold expression with and, that's what's evaluating this part. And then when we return, when we actually dereference and pass it to strucat as the function, that's what's evaluating that part. Everyone following? Yes, question?
So is it necessary to store the result, or can we just compute it?
Is it necessary to store the result and compute it? Well, I think it's necessary to store it, but the compiler can see through this usage. I'll answer that more fully in a few minutes. We'll see how it shakes out. Okay, so this is what the code looks like now. It looks exactly how I wanted it to. Lazy call of foo with I, lazy call of bar with I, and we still have to wrap the thing because of format. So maybe this is better, maybe this is not. If these functions are really cheap, maybe you just go ahead and call them anyway, right? If they're just returning optional ints or something, you can really take your pick. So lazy evaluation is on the table if you want to use it, or you can go ahead and use eager evaluation. It really depends. Now, question I got from someone the other day. Does the optimizer see through all this? And at the time, the answer was no, because I had implemented this slightly differently. But I went away and implemented it this way. And, simple code, the optimizer can see through it, at least in my experiments, which admittedly are sort of micro experiments. So do you all agree with this slide? Do some of you disagree? Maybe some of you disagree. But it's an argument we can have later in the bar, perhaps. I think we're doing pretty well. Question, Peter?
I thought we were talking about applicatives, where you had like a function inside of a functor, and the Variadic fmap, the function is not inside of a functor.
Right. You thought applicative meant a function inside a functor. But what I'm telling you is that applicative means being able to apply functions in more than one argument. In Haskell, it means a function inside a functor. But the reason it exists is to apply functions of more than one argument, and we can express that better in C++ than currying. Good, thank you. That's what I want to make very clear in this talk. Another question.
Dumb question, but is that fundamentally the same thing? Or?
Is that fundamentally the same thing? Yes. The reason applicative, well, Lisa might argue with me later. but in practical code, the reason applicative exists is to be able to apply functions of more than one argument to multiple functorial values. And in Haskell, that's achieved with currying. And in C++, I think we can achieve it better. Is that Patrick?
One downside with the lazy call is that, like the fmap, you can't pass a function overload set. So
Yeah.
without wrapping it in a lambda.
Yeah. I mean, this is C++. So if you want to handle function overload sets, whatever, maybe. Lisa, did you have your hand up? Sorry, this light's way in front.
Since you brought me into it, I'll tell you the only argument I would have is, it is a little different in Haskell because you don't have to go through the whole currying process. You can stop part way, and in C++,
Right.
you can't.
Good thought. Yes, Haskell is lazy by default and has currying built in, and so they express it that way. I think this is a better way in C++ to express it, and we'll see. The rest of the talk is all about how this shakes out. Let's see. So we did optional, right? Optional is kind of easy mode. Let's take a look at expected. It's a little bit trickier, but not a lot trickier, hopefully. David.
I guess the question of whether or not they're equivalent could be answered is if you can implement one in terms of the other. Have you gone through that?
Yes. If you could implement one in terms of the other. I haven't tried that in C++, and no, I haven't tried it. So it's an open question. But I think I come from a pragmatic place, right? So I think the formulations I'm giving in this talk are applicable to practical code in a way that currying is not in C++. Tobias.
Yeah, I'm not sure, but will you overload on fmap for different functors?
Will you overload on fmap for different? Yes. So it doesn't have to be overload, but what's doing the job of fmap? It's a different function for each functor.
Yeah,
right?
will you call it always fmap? Will that work?
We'll always call it fmap at work. I don't care. Not
Okay.
not important for this talk. You can call it whatever you like. I don't really mind in your code base. Okay, let's move on. So the question is, can we make this code work the same way for stood expected? And of course, this is a presentation, not a headline, so you know the answer is yes. So this is exactly the same code, except now, instead of optional, this is an expected of string and e, right? And e is something, don't care. What do we need to do to make it work for expected? Well, the success case looks a lot like optional, right? We're taking in some expecteds, and we have to do some rigmarole to like strip out the t's, right? The t is the result of applying the function to the success, and the error is, you know, something that recovers the error. If the same error is in all of them, then it could be maybe simpler than this, but this does the job, right? I'm going to expose error t later on. The return type of this function is what you get when you invoke that and stick it back in an expected, right? And here's the success part. Looks very much like optional. So we're just going to do the and fold, and then we're going to invoke the function. OK? And let's see now. When we, and this is the success part of lazy for expected, right? So again, very much like optional. Here's the function. Here's the result. Now, one thing's different, I guess. Expected, and this is a bit of C++ism, like we're assuming the expected type is default constructible, but there are ways around that, and this is slideware. So, but again, when we convert to bool, that's when we're going to call the function and tell you if it succeeded, and then assuming it succeeds, when you dereference it, you're going to get the thing out of the expected, or you're going to get the expected value, right? And here's where I expose the error type. That's just from the underlying expected.
Question.
Question, yes.
Didn't you say earlier that your, I guess, exp would be, with the optional case, was like an optional result?
Yeah. So the function that comes in here is like the foo or the bar, remember?
Mm-hmm.
And in the optional case, they return optionals. And in this case, they return expecteds. So this guy is an expected. Does that answer the question? That make it clear?
Oh, I see. OK, that makes sense.
OK. The error case. Well, we're using an and fold, right? Where that fails, like anything after that's not evaluated. So we need to use another short-circuiting fold to recover the error. So we've got another short-circuiting fold, which is called OR. What we're going to do is wrap the lazy values in a very cheap type for the purposes of inverting them. So when we convert this guy to a bool, it's going to say not has value. And when we dereference this, not with a star this time, but with the actual with error, we're going to get the error out, right? So that's the plan. Invert the sense and use them in the OR fold. And this is a bit of C++ machinery, I know. So here's the error case, and it's kind of unfortunate the way we have to write these fold expressions, but here's the fold, and we have to do this thing where we invert and then extract the error from it. Right? So this is going to short circuit exactly as far as it needs to, and no more. It's going to evaluate as far as it needs to. When we hit the thing that failed, it's going to actually be true in the OR, and it's going to get returned. Right? But this extraction is a little bit awkward, but we only have to write it once. And we know it's safe to do that because the short circuits exactly match each other. And now the code works. We get exactly the same call type as with stood optional, except that now they return expected. And again, the question is, does the optimizer still see through all this? In my admittedly micro experiments, the answer is still yes. OK, so what's the conclusion? Well, P2561 says, does C++ need an error propagation operator? And the answer is still maybe, right? Because C++ is full of things that could be better in the language, but we did it in the library. But I think it's important for me to show this because we need to think about this in terms of having this conversation, because this is what applicative is for, right? Applying functions of more than one argument. And so I think the best case today does not involve macros, but is something like what I've shown. OK. Questions? Anything more before I move on? All good, Barry?
I would write the macros.
You'd write the macros. OK, well, you know. This C++ is large. It contains multitudes. OK. How about asking about applicative versus monad? This is like the question of, should you use pushback? Should you use in place back? There are folks who say always use in place back because it's strictly more powerful. And every monad is an applicative. So should you just always use monad? Why wouldn't you? It's a question of power, right? So every monad is an applicative. And yes, in a sense, monad is more powerful than applicative. You can do everything with monad that you can do with applicative, but more power means more constraints. It's more powerful because it's more constrained. And so what does that constraint mean? Well, I showed this code. The monadic operations on optional, or indeed on expected, as we're going to get, can solve this problem as well, but not better. And not only not better because the code looks bad. So what's the real difference? What is monad for? This is what I want to kind of really express with this talk. What's applicative for? What's monad for? Monad is for when you need to make choices based on what came before. When you have data dependencies. Monadic bind is inherently serial, right? That's what monad is for. Applicative, on the other hand, is not. We used fold expressions at short circuit, but that was an engineering choice, right? If we want to, we can evaluate all of these in parallel. That's what applicative is about, right? As opposed to monad. And that's how to choose between needing monad and needing applicative, right? Use monads when you need that data dependency, when you have to make a choice based on some earlier computation. Otherwise, why would you constrain yourself to serial operation, right? And this is how functional programmers think about architecture. I learned some of this stuff when I was, maybe it was, early teens, and at the time I had a long commute. I was driving every day between Redondo Beach and Irvine, which is like 40 miles on the 405. It's like an hour, 20 minutes each way. And I was listening to functional podcasts, and I was thinking about this stuff. And what I heard these programmers saying on the podcasts was things like, when I was thinking about this problem, and I knew I needed, to make this decision based on this computation, so I knew I needed a monad. Or I knew, they were thinking about the problems in terms of these patterns based on parallelism, serialism, right? And making that choice. OK, any questions? No questions. Oh, one question.
So all monads are applicatives.
Yes.
Can you give an example of an applicative functor that is not also a monad?
Oh, this crowd is great. We're coming to that. An example of an applicative which is not a monad. Yeah, we'll get there. In fact, it's the very next section. So let's look at some more. So we've seen optional, we've seen expected. These are like baby's first monads, right? Let's look at sequences, right? So we can observe that a range is a functor, right? And an fmap is transform, just like it is on optional, right? So what's a signature of transform? We give it a function from a's to b's and a range of a's, and it returns a range of b's. I mean, that's the signature of stood ranges transform. I never remember which. Is it stood ranges or stood views? Stood views transform, probably.
Can I inject a comment?
Yes.
You can think of an optional as a range of either length 0 or 1.
Yes, indeed you can. Yeah, an optional is just like a range constraint in one view, yes. Steve?
Except you can't.
Except you can't.
I'm working on fixing that.
Cool. Maybe we could say platonically, you can think of an optional as a range of 0 or 1. Yes.
You can in Rust.
Yeah, so this is what fmap looks like. This is what transform is. It implements fmap, right? So we can get some ints and we can square them. No problem with that. We can also observe that a range is a monad, right? How would we implement bind? Well, we actually have join. So we'd implement transform followed by join, i.e. fmap followed by join. And here's the signature of bind. And a use case for this might be in min-maxing a game for the next best move, right? So we've got a function which takes some game position, gives us back a range of new game positions, and we can compute possibilities for the next move by, well, this is just sort of one step of the process, right? But given some boards, in this case there's only one, we'd run the transform. That would give us a range of ranges, and then we join them, right? That is bind. That's implementing bind, right? Transform followed by join, and then we could go down another depth, right? To look at the next, based on all of those next possible moves, what's the next possible reply, and so on and so on. So you can chain that monadic operation. Everyone good? Ranges are functors. Ranges are also monads. Now, yes, we know that every monad is an applicative. So how is a range an applicative, right? So we've got these two functions. We need to write this function, right? We need a function that takes a range of functions and applies them to a range of values. Or in our alternative formulation, we need a function that generalizes fmap, right? So we need a function that takes a function of more than one argument and a bunch of different ranges, right? Can anyone think of a function we have that takes a function and n ranges and applies that function across each element of the n ranges?
Zip transform.
Zip width.
Yeah, zip transform. Did you say that? I think I heard you say that. Zip transform, yes. Zip transform applies this function to each position of the ranges zipped together, right? So, ranges zip transform view is an applicative functor. Let's check to see if it's a monad. Let's go through the types. Again, I'm writing in Haskell because otherwise you'd be overwhelmed by templates. So f1 and f2 are functions that return ranges, right? And we're going to zip these together. This is fmap, right? This is infix fmap, right? So we're going to zip the range of f1 and f2 with the values a and b. Now, when we apply f1 to a, it's going to return some range. f1a, f1b, f1c, I've said here. When we apply f2 to b, it's going to return another range. How can we join the result? Well, we could just join them. But it turns out, like, as you can see, when we apply these functions, they can return ranges of different lengths. And in order to be a monad here, we need to obey some laws, which I'm not really going to mention, but one of them is associativity. And that is commonly the one that gets broken here if we just join these naively. One way to do it would be to take the ith element from the ith list, from the ith range in that range of ranges. And we could do that if those functions returned constrained ranges, like maybe infinite ranges or at least ranges that go up to I. But we don't have that. We don't have that constraint here. And like I said, all the other ways we can think of to join these run afoul of the monad laws, usually the associativity law. So zip transform view is an example of something that is an applicative functor but not a monad. So let's try again. We have another function with almost this signature, and it's called Cartesian product. And in this case, it doesn't actually take a function. It just takes all the ranges, and it zips them together every which way, right? It does the Cartesian product, and the function here really is the function is implicit that we're passing in, and the function is make tuple, right? So it returns a range. It returns a range of tuples, and each tuple represents the, the Cartesian product of these ranges. So, yes, this is what Cartesian product does. It takes a bunch of ranges, and it returns us a range of tuples. And so, for example, if we would do it on a 1, 2, 3, and ABC, we'd get the sort of cross product, the Cartesian product. And it's implicitly applied make tuple, but we can then fmap another function onto that with some suitable formulation of std apply to apply it to the tuple, right? Range's Cartesian product view is an applicative functor. Is it also a monad? Well, in this case, the answer is yes, right? Because it turns out that this is just fine if we were to take a function that returns a list here and map it over the Cartesian product view to get a range of lists, then we do satisfy the monad laws just by joining those lists. So Cartesian product is a monad as well as being an applicative functor. Now, in case it escaped your notice, this is a list comprehension, right? This is exactly the same formulation structure as a list comprehension. Cartesian product is what list comprehensions look like in other languages. In C++, we don't have a great syntax, but it is the same thing. Anyone want to challenge that view? Everyone good with that? All right. Yeah, ours are a bit more verbose, but it's the same formulation. All right, good. I think we're doing pretty well for time. All right, let's have a bit of fun. Well, at least it was fun for me. May not be fun for you. So, we have Cartesian product on ranges, but ranges are homogeneous, right? So I thought, can we make Cartesian product for heterogeneous ranges, i.e. tuples? And because I'm asking the question in the talk, the answer is yes. Now, how might we do that? Well, first of all, what do we want it to look like? We've got 2 tuples, and we want to do a Cartesian product on them. So what are we going to get back? We're going to get back a tuple of tuples, and inside that tuple, each one will be, the result of doing the Cartesian product, that part of the Cartesian product. So we can get a bunch of tuples whose head is A, and then whose head is 1, and then whose head is true. And then the second part will be us mapping across the y's here. Everyone follow? Now, undoubtedly, it's unfortunate that Chris and Daisy are doing another talk while I'm doing this, because I'm sure they could cook up something way better than what I did. But I went the easy way, and of course I made a recursive solution. And we can kind of see how that's going to work if we look at kind of going backwards from like 2 tuples to 1 tuple to no tuples. When we do a Cartesian product of 2 tuples, we get this. Cartesian product of 1 tuple is just the tuple of tuples of each element. And so that leads us to the conclusion that a Cartesian product of an empty tuple is a tuple containing an empty tuple, which sounds a bit weird when you first think about it, but this is what falls out of the natural sort of recursive solution. I think Steve agrees with me. I see him nodding.
Yeah, I have to write a paper for it.
So let's sketch a recursive algorithm. So we're going to get, yes?
Why, when you define the Cartesian product, you decide to lose the matrix structure of the result? I mean, there is more structure than this if you want, right? You could set it up as a matrix, adding more curly brackets there, and then flatten that if you need. But
if I understand I'm not sure I understand the question.
So you could add more structure to the result of Cartesian product if you imagine that the result needs to be a matrix, right?
I see. So a Cartesian product could be yes, you could do a multi-dimensional thing, right?
One more. One more level, I think.
Yes, yeah. Cartesian product in general could be represented as one more dimension. Exactly. Yes.
That information is lost here.
I did it this way because it matches the way we do Cartesian product for a range in C++, and this is just another range. It just happens to be heterogeneous instead of homogeneous.
It is true for ranges too.
Yeah, it is true for ranges. Yeah, but I'm matching the sort of interface of C++ standard. Okay, so if we think about a recursive algorithm, what are we going to do? Well, we're going to do the classic recursive thing of like the first tuple and the rest of the tuples. And we're going to say, let's do the Cartesian product of the rest, right? And then what are we going to do? Well, for each element in that first tuple, we're going to prepend it to each element in the Cartesian product that we got, right? And then we're going to just kind of collect all those together. If there are no tuples left, we return, like we said before, the tuple of one empty tuple. And here's the wall of text that results. But you can see, here's the base case, tuple of one empty tuple. Here's the recursive step. We've got the first one and the rest of them, and we take the Cartesian product of the rest. And then we're going to prepend for each element of the first tuple, we're going to prepend it here to the rest with a bunch of tuple cat, tuple make tuple, forward as tuple, etc. But this works. This does what Cartesian product does, but on heterogeneous sequences instead of homogeneous sequences. By the way, have I mentioned how annoying this? So, what's the return type? What's the type of T here?
Tuple. One empty tuple.
Empty tuple. Yes. If that was a surprise to some of you, count yourselves lucky. This is an unfortunate. When you're writing code like this, and you have to write this instead. And now, twice this has bitten me in generic code. Yeah, this is an unfortunate thing that falls out of CTAD. This is like engaging the copy constructor of the outer tuple. Yes, yeah.
Which you never want.
Sorry?
Which you never want.
Which you never want. Yeah, you almost never want this in generic code. Like, at first I wrote tuple containing tuple here, right? And it didn't work. And I debugging this by building up tests. And I'm like, oh, this again. Yeah.
And the worst part is that adding curly brackets doesn't help either. Inside.
Yeah, adding braces doesn't help. This is like CTAD works on this, and you get the copy constructor. Okay, so this still uses make tuple, but let's generalize it a bit, right? We could pass the function in directly rather than using make tuple, and that might actually be easier. But the wrinkle here, and the reason I started with curry, is that make tuple actually is sort of masking the fact that we're building these up in reverse, and we're partially applying make tuple because, of course, make tuple takes a Variadic pack anyway, so that falls out. So in order to do it with a general function here, we will need to flip the currying, right? We'll need a currying operator, which this is exactly the same as the one you saw earlier, except the order of arguments here is flipped. So instead of saying args and then a's, the args that are already bound, and then the new arguments, those are flipped around. Otherwise, this is exactly the same, right? So because of the way we build it up recursively, we're going to bind the arguments from the back. And maybe I could have used bind back or something, but anyway, I had curry, so I just flipped it. And then it looks like this. Again, much the same. Instead of, in the base case, we're just going to partially apply with no arguments, right? We have no arguments at this point. So we're getting back the function which will take the arguments from the back, as it were. And then the recursive case here, instead of all that forward as tuple and tuple cat, we're just calling the function. I didn't put std invoke here, but I could have. But it would have made more noise, I suppose. So yeah, that's the general version, that's the tuple version. General version, tuple version. So you can see they're just the same structure. It's just what we do here and what we do here, which is different. Anyway, I just did that because I thought it'd be interesting. And we can, C++ is very expressive. It's not always very beautiful, but it's very expressive. Okay, good. Any questions? No. All right, we will move on. Let's look at even more applicative. So we've looked at optional, expected, ranges. I want to show a couple more fairly briefly. One of them is parsing. This is, in fact, I think, like one of the original use cases for applicative and the reason why it was sort of separated from Monad. So you will all recall that a parser for things is a function from strings to lists of pairs of things and strings. If that seems clear as mud, what that means is, it's a funny phrase, but a parser for a t, an int, whatever, let's say an int, takes a string, right, or something the same as a string, like a string view, right? Take a string, and what do you return? You return a pair of that int and the leftover string after you've parsed it out, and a list of those because there might be multiple ways to parse, right? In the general case. So that's an explanation of that. And in C++, this is the same function signature. I'm using string views. And yeah, I'm going to return a range of, this is pseudo C++. I'm going to return a range of pairs of t's and string views. So that's what a parser is. Yes?
What do you mean by multiple ways of parsing?
In the general case, you might interpret the string in different ways.
Okay.
Yeah.
Even ints?
Commonly, in most grammars, commonly we'd want to say return an optional AN string. The parse either succeeds or it fails, right? But in the completely general case, it's a list. This is like the comment earlier, like optional is a range of at most one thing. Very similar. So 6 years ago, I was stood on this stage with Jason, and we presented context for all the things. That's an age ago now. And in that talk, I had this function, which I used to combine my parsers. And the type signature of this function, you can see it takes two parsers and a function. And whatever comes out of those parsers, so this might be an int and this might be another int, it will combine them with the function. And the return type of this is unstated here. But this returns a parser of the return type, right? Because it's a parser combinator. In Haskell, it looks like this. You take a parser of A's and a parser of B's, and a function which will eat those A's and B's and give a C, and what you get back is a parser of C's. Now, this function signature should look familiar. If we flip the arguments around, this is fmap2, right? If we think of parser as being the functor, here's the function of multiple arguments, 2 arguments. We've got 2 parsers, and we're returning a parser. This is fmap2, right? This is a formulation of applicative, albeit a very constrained one. And then in that talk, mostly I used combine in one of 2 ways. I basically wanted to either throw away what was on the left-hand side, and so I did this, or I wanted to throw away what was on the right-hand side, and so I did this. And I just overloaded operators less than and greater than to do each one respectively. And so then I could write code like this. How am I going to make a string parser? Well, a string parser is a quote parser followed by a parser for a bunch of things which aren't quotes, followed by another quote parser. But I don't care to keep what these quote parsers return. I know that strings are surrounded by quotes. And that's why I'm using this less than and greater than. These are just fmap2s, if you like. These are applicative operations. And I give you one guess where I got this technique. I didn't make it up in 2017. Although it may have been new to some folks, I got it directly from Haskell, right? Where Haskell has these operators which do exactly the same thing. They keep what is on the right, what is on the left here, or what is on the right here. And Haskell can make up operators out of whole cloth out of any kind of characters. So they have these stars in, and they point to the thing that gets kept. But in my case, I kept the thing that was bigger, as it were. So what does it look like when you parse with monads versus when you parse with applicative? Because, like I said, this was one of the early use cases for applicative was parsing, because you often don't need the full monad. Well, in Haskell, this is what monadic parsing looks like. And I put it in Haskell because if I wrote the C++, it would go way down there somewhere. But what this is saying is, this is using do notation, and this is sort of a shorthand for that nesting of monadic calls, right? So you parse it, this is to parse a hex digit like 0xab, right? A hex number. So you parse a 0x. You don't care to keep that because it's not part of the information you want to store. You can parse out the high nibble with a hex digit parser. Similarly for the low nibble. And then you call hexify, which is a function that takes those two chars and naturally, gives you the int that this represents. You call hexify on it. And return here isn't, I don't want to get into that, but return just means the same as pure. It lifts the value back into the monad. It's nothing to do with C++ return, function return. If we were to write this in C++, this do expands out to like call the thing, nested call, nested call, nested call. It would look truly horrible. It might be better if we had like pipeline operators and things, but we don't yet. With applicative code, this looks much more declarative. This is just saying, I want to apply hexify. How do I want to apply it? To the result of parsing the first hex digit and parsing the second hex digit. So this is just combining these two with applicative, right? This is fmap. This is apply, right? We saw a slide way earlier which was applying plus. This is doing the same thing, applying the hexify function. This time, instead of being the optional applicative, it's the parser, right? These things are parsers. And we're combining them together. And it's nice and declarative. So parsing is one of the earliest things where applicative was used a lot. And it's because it's almost always all you need. If you have a sensible grammar, you only need a monad if you need to have that data dependency. But if you have context-free parsing, you probably don't need the monad. You just need applicative. And when you can not use the monad and use applicative instead, it's better. OK. Let's talk about asynchronous execution, right? So C++ has P2300, which is a proposal for senders and receivers. I'm pretty sure that the authors of that paper made every attempt to avoid using any functional programming terminology. Maybe they didn't want to scare people off, which means that people like me have to go fishing in the paper, right? Sorry?
Yeah, going hunting for bind.
Exactly. Luckily, it's not too hard to find if you know where to look. Here's Eric talking about this, and he had this slide in his talk showing not all of the different sender adapters, but a fair few of them. And now that we know what to look for, we can see what's there. Then transforms the result value of the operation with a function. That sounds a lot like fmap. And then the curiously named letValue passes the result of input sender to function, but it's a function which returns a new sender, right? It's returning a monadic thing. That sounds a lot like bind to me. And when all is applying to multiple senders. It's taking multiple senders and waiting for them all to complete and then applying a function to what they return. That sounds a lot like the formulations of apply that we've seen. So this is what P2300 does. It has then, it has letValue, it has when all. It even has just, which just sends the provided values, which is equivalent to pure or fmap 0, right, that we saw earlier. And if you're used to functional programming, then thinking about it in these terms is, I promise you, easier. And this is how we know, at least in part, that P2300 is a sound design. It's not dreamt up by architecture astronauts. It's based on functional principles that have been known about for decades. So we know it has the expressive power that we need. And this is a really good example because more than any other formulation, this really highlights the difference between applicative and monad, right? Monad is inherently serial. Like we saw earlier, you could implement when all with let value. You could do that, but it would involve serializing every operation. That would obviously be wrong in the context of an asynchronous execution framework, right? So every monad isn't applicative, but you don't want to use monad if you don't have to. Yeah, so let value has a data dependency on its argument, right? You kick off a new sender based on what let value returns, and you can choose which sender to kick off. That's a monad, right? That's what bind does. When all is the generalization of fmap we've been seeing, and it can run all its input senders in parallel, right? And then combine the thing, right? And like I said, it would obviously be wrong to implement when all with let value. It can be done, but it involves serializing. Okay, so what's the conclusion here? To summarize, I have shown a bunch of different applicative instances, how they work, including some that are, one at least that is not a monad. And there's a bunch of them in C++, and when you start looking for them, you see them everywhere. I didn't have time to cover a bunch of other things. Validation is very similar to parsing. It turns out that function application itself, which in Haskell is called the reader monad, is a monad, is an applicative. And there are many, many more examples. So given what I've shown here, should we just forget about monads and try and always use applicatives? Well, we should use applicative where it makes sense, right? We shouldn't throw away monad. It is more powerful. Sometimes we need it. But the thing is, if you've got a monad, great. If you only need an applicative, even better, right? This is a quote from Conor McBride and Ross Patterson's paper. So when we're thinking about functional architecture, we should think not how these patterns are implemented, because usually that's based in Haskell, and that's not suitable always for C++. We should think about what the functional patterns are for, right? And fmap, or functors, what they're for is working on values without opening the box, right? Applicative is for combining multiple values in the functor. And monad is for making that data-dependent choice, being inherently serial when you have that data dependency. So, C++ is not Haskell, so let's stop thinking about these things in terms of their Haskell formulations. Thank you very much. Questions? David?
So I think that when it comes to functional patterns, we should think about what they are, not how they're implemented in Haskell or what they're for. And in this case,
okay,
I think that what you're saying is applicative is not actually applicative, because you're only allowing the application of functions that have been lifted from the outside.
Okay.
You're not allowing for functions that are on the inside to be applied. And an example of this would be in your parser applicative to be able to parse some text into a function and then apply that function to other parse texts. So it seems like what you have is something in between fmap and applicative. So it's a different category of things that's not as representative.
Okay.
Yeah.
Sure, I'll take that. I would contend that what I've shown is far more useful in C++ than the function inside the functor interpretation.
Well, let me respond to that, because what you've said is applicative is less powerful, but anything which is actually applicative, you can create that function that you put there. So
sure, but we can implement currying in C++. It's just that it might not always be the best thing. If applicative requires
hold on,
the function inside the functor, and most cases requires currying.
No, I think that the function that you're using is very useful and is the best way to do that in C++. Like, I'm totally down there.
Right.
And that can be implemented in terms of the the operations that you get with an applicative functor.
Yes. Yeah, I agree. Yeah, you can implement all this stuff in terms of the Haskell implementation of applicatives. That's what you're saying, right?
Yeah,
The one
just
can
not the other way
implement
around. So that's
Sure,
why
sure.
it's a different category.
Okay. Yeah. But I mean, I still would stick to my idea that, like, the raison d'etre of applicative is to generalize fmap. And so I think if we want to do that, this way is better in C++. Okay. Barry, you had a question.
Yeah. So where I'm a little stuck right now is, okay, so you're saying applicative is for parallel application, monad is for serial application.
Yeah.
And then you have the parser example.
Mm-hmm.
But like, if I'm parsing a hex digit, like I need to do these things one at a time, right? Like I need to parse out the 0x and then the first digit and then the second digit. And when I have all these pieces, I can turn that.
Yeah,
but each one of these things can fail serially.
Yeah, but applicative, well, they don't have to fail serially. They can fail in parallel, right? The parser you're going to run to parse the second hex digit, you already know. It doesn't depend on what the first digit was.
Okay, so just because in this case, I happen to know that all three of these are fixed
Yeah,
length.
you're parsing a hex number, so you know which parsers to run. You don't make a choice about which parser to run based on based on the value of something you've parsed. That's why it's applicative and not monadic. You're still, you can make a choice about whether to run those parsers in parallel, whether to run them serially, but applicative doesn't impose the choice of seriality.
The dependency is not on the data to parse. It's on the choice of parsers to run. Is that correct?
Yeah. Well, there are plenty of examples, of course, of context-sensitive grammars where the parser you want to run depends on what was parsed, depends on the value of what came before. And that's a kind of monadic structure. Steve?
Yeah, even you can still, with applicatives, build choices in your grammar. It's just this parsed to nothing.
Yeah,
And
exactly.
then you go down the other side of the choice. But that's still not choosing which parsers to run. You're saying, okay, which parse was successful?
Yep. Peter?
Coming to the motivation for the error operator specifically, even if the subsequent operation may not depend on the result of the last operation, the data that, the arguments of the second operation often do. And so I would think that having that data dependent structure would be extremely common in the error case. For example, I
It may well.
define what is the name of the database that I'm going to, what is my name? Do I get a
yes.
name? Connect to the database? Did I get the database?
Yeah. You're right. There are plenty of examples if we go looking of where we need the monadic structure because what comes after depends on what came before.
Especially for errors.
Especially for errors, but not for errors in this case, which was why it was a good foil for the talks. All right, thank you all very much.